Well, hello again. Today we're going to have a look at graphs of gradient functions. So we know how to algebraically find the derivative or gradient function, but today we're going to have a look at our pictorial approach as far as what the graphs of the gradient functions look like given the shape of the original functions. Okay, so looking at an example here, a simple example, we've got y equals x, okay? So we know that if y equals x, we know that the dy dx, or the derivative, equals 1. And that means that the gradient of that graph is always 1, doesn't it? Yes, it does mean that. And therefore, we would expect the gradient function would be a line which always has the value of 1. And that red line does exactly that, okay? A flat line, constant gradient of 1 with a y-intercept of 1. So that's a nice easy one, okay, just to get us warmed up. Have a look at this one now. We've got y equals x squared. So we know that if y equals x squared, dy dx equals 2x. Of course it does. And therefore we're saying that the gradient function is 2x. So that is a linear function, isn't it? Yes? So you know what that looks like. Well, we're going to have a look at a geometrical approach now. If, for example, they didn't give us the equation of the blue function there, they just gave us the shape, and we had to work out what the shape of the gradient function was. The first thing we would notice is that at the origin there, I've drawn a little purple line, which isn't very easy to see, but that is indicating that the gradient of that blue function there is 0. It's flat at the origin. Therefore, the value of the gradient function is the value of that gradient at that point, which is 0. So we plot a 0 value for the gradient function. And then if we just go round to a few points on that blue curve and examine what the gradient is, for example, that point there that I've just marked in purple, if you now draw a gradient, a little gradient slope line at that point, a tangent line to the graph, then you say, gee, that's a pretty negative looking gradient, isn't it? Well, therefore, you need to plot for the gradient function a negative value of that gradient as the value of the gradient function. So I'll do that now. I'm just guesstimating this. I don't know exactly what it looks like, but I'm kind of fudging where I'm putting these because I know it's supposed to be the line y equals 2x, so I've sort of worked out and lined up my points so it kind of works. But, you know, you're only supposed to do a guesstimate, an idea of these things if they don't give you the actual equation of the original function. Now, let's have a look at another point, which I've drawn in there, where it's -1 and 1, okay, that purple dot, cross that I've showed there. Now I'm going to draw the tangent line on there. It's less negative, isn't it? Less negative than the one before, so we'll put a less negative gradient value point to reflect that. You see how it's working? Okay, now, when we've already got our point at the origin, our red cross there to depict a 0 gradient at that point, let's do a couple of positive ones. Okay, that point there at 1 and 1. Therefore, we'll do the slope line. There it is, and that's a positive gradient, no doubt about it. So let's plot in a positive point to reflect that gradient. There it is, okay? It's looking pretty good. I can see a straight line sticking out a mile, can't you? Okay, one more, I think. Okay, that purple cross up there, we'll put the slope line on it, and then we'll put a red cross to denote at that value of x what the gradient looks like, okay? And it's something like that. So you can see we've got a beautiful straight line curve of best fit, and or line of best fit, and let's put it in. Wow, pretty good, eh? So that's how you do these things, okay? That's how you work out geometrically what the gradient function looks like. Let's do, what's that say? Yes, it's a gradient function. Of course it is. Now let's do another one. Y equals x cubed. All right, let's do the same thing there. Now the first point I always start with is the points which have a 0 gradient. So I've just marked it in there at the origin again. So that's going to deserve a point of 0 gradient, okay, for our gradient function. And there it is on the red cross right on the origin. Now, looking to the left of the graph, there's a point. Let's have a look at the gradient. Very positive, highly positive. So we need to put in a highly positive point for our gradient function at that value of x, okay? And there it is. Okay, moving right along, there's another point there for us. That's looking a little bit less positive, in fact quite a lot less positive than the last one. So we need to, for that value of x, which looks like x is minus 1, we need to put in a value for the gradient function to reflect that, which it'll be less, much less positive, okay? But still positive. Ooh, that looks all right. Now we're going to go for a point, it's pretty hard to see, about a half, I think I've put in there. Yeah, I've drawn a gradient line there, and we're putting in a less positive point again for that still positive gradient at that value of x, being about minus a half by the look of it. Look, can you see a parabola happening? I can. And you're getting the drift by now that the degree of x of the gradient function is always 1 degree less than the degree of the original function, isn't it? So yeah, there's about a half, and I'm going to do the gradient half value of x. I'm going to do the gradient line now. There it is, and it's positive now. It's positive, so I'm going to put a positive value in for my gradient function at that value of x. Yes, looking very parabolic to me. Here comes another one at about x is 1, and here's your slope line. Oh yes, getting much more positive. So we'll put a much more positive value of x in. Of gradient function in for that value of x, and one more. There's about x is 2 by the look of it, and it's very slopey there, and it's very positive, highly positive. So we'll put in for about x is 2 a highly positive gradient value, and we're just going to put the line of best fit in, and parabola, beautiful, isn't it? So that's the actual. And we got it right, didn't we? We got the trend. Okay, another one. Oh, goodness. This is a cubic, and I've started off already. I'm so keen. My little computer put in my 0 point there, my 0 gradient at the first local maximum, and therefore I'm going to put in a 0 gradient value point at that value of x. Now, here's another 0 gradient, so I'm going to do the same thing there. 0 value for the gradient function at that value of x. Now, it's point of inflection time, folks. Now, in case you don't know what a point of inflection is, it's the point where you've got maximum slope of one direction before it starts to trend towards the other direction. Now, I'll explain that in a minute. But that's the point of inflection. And that's very important because that tells you that value of x, you are going to have a local maximum or minimum on your gradient function. So it's very important to line your point of inflection up for the appropriate value of x to get the value of x for your local maximum or minimum of the gradient function. Now, over on the left, I've tried to show you a very quick little diagram of the point of inflection. It's where concave down meets concave up, or vice versa. Now, by concave, I mean, think of that little, those two little shapes as caves. One's pointing downwards to look out of the cave, and one's pointing upwards to look out of the cave. And you can see the point where they meet is the point of inflection, because that is the point where the gradient stops trending. In that little example I've given you there, stops trending into being more negative all the time to the point of inflection where it starts to trend to become more positively inclined as the x increases along. So you get to recognize them very easily after a while. You can see the concave up and the concave down in that blue function. And the point of inflection is the point where those two caves meet. Okay, so I'm going to put later on I'm going to put a point of inflection when I figure out what this gradient graph is doing. Okay, now that's what I said, local maximum or minimum for the gradient function. Oh yes. Now let's pick some slope points here. Right, very highly positive. There, woo! So we need a very highly positive value for our gradient function at that value of x. There it is, yeah? We're getting this. And of course, if we've got a cubic, we're kind of expecting a parabola, aren't we? To the x to the power 2 for our gradient function. Okay, now let's do another one. Okay, that point there, that's still positive, but nowhere near as positive as the one we just did. So we need a less positive value for our gradient function at that value of x. There it is. I get the trend. I get the trend. Do you? It's going to come down there, and then at our local point of inflection, our point of inflection, there's going to be a local minimum. I can see it sticking out a mile. Can you? So I'll just put one in. Good show. Now, okay, I get the shape now. Do you? It's just going to go up the other side now. But let's just prove that. There's a point there, and it's got a very highly positive gradient, so we need a highly positive value for our gradient function at that particular value of x. So put it in, and I think we're all ready to go. Let's plot. Shoo-hoo! There it goes. Very good, isn't it? See, it's easy as when you just get into the rhythm of this stuff. There you go. Beautiful. So, all right, another one. And now that's a negative cubic now. Okay, same procedure. I'm getting better at this now, so I don't need to draw all those slopes anymore. I can just kind of get it, okay? So the zero gradient points, there's one. There's zero gradient function value. Zero gradient point, zero gradient function value. Point of inflection, that means local max or min for the gradient function. Let's just work it out, what's going on. Yeah, I've kind of predicted what it's going to be. I've given the game away. I've just plotted the point in. But you see, this part of the graph has got a negative gradient, so therefore the gradient function's got to be negative for all those parts of the graph where the slope is negative, yeah? And that's right. So also, oh yeah, that part of it's too. That's negative too. There's negative gradient. So we're going to have negative values for the gradient function for those same values of x for which that gradient of the graph is negative, yeah? Now here are the positive ones. Gradient's positive, and therefore the gradient function values are positive for there and for, oh, wait a minute, just go away, I'm not ready for you yet. Yeah, so therefore the gradient function is positive for just that part, yeah. There's only the middle part of that graph is where the gradient is positive. So, yeah, now there comes the graph to reflect that. Zoom, very nice, very nice. And there it is. Beautiful, beautiful. Okay, you happy? This is pretty easy, isn't it, really? Let's go on to another one where we've got the, oh, goodness. A quartic, gracious me. Well, there's 3 points on that graph which have zero gradient that I can see. And of course we're expecting a cubic shape. There's that one taken care of and its gradient function point. There's that one and there's its gradient function point. There's that one and there's its gradient function point. Now, we've got 2 points of inflection. Can you spot them? Can you see where concave up meets concave down, or concave down meets concave up, and pick the middle point in between one cave and the other, like where one cave starts, you know, one finishes and one starts, if you know what I mean. The gradient is negative the gradient function is negative for those parts of the graph, yeah? That's where the gradient is negative. Get that? And the gradient is positive, therefore the gradient function is going to be positive for those 2 parts of the graph, yes? Okay, now here comes our points of inflection. There they are. Did you see them? Halfway between those caves where they join onto one another, yeah? So they get us local maximum or minimum values. Now, we just got to get the drift of the way this function goes to work out whether they're going to be maximums, maxima, or minima. Got to get my Latin right. Now, let's see, what do we think this is going to do? Well, the left-hand side of the graph, the very left-hand side, is got a negative gradient, so it's going to be a negative value of the function. I think this is going to be a right way up cubic, if you know what I mean, coming in from bottom left and going out from top right, like every good cubic does if it's a positive one. Yes? Let's see. What have I got there? Yes, that's right. They have their local maxima or minima for the gradient function, for the points of inflection, for that value, for those values of x. I've plotted them in there. I sort of worked it out while I was thinking. So here we go. There, just what I thought. Just what I thought. Do you get that? Do you agree? If you look at that, you'll see that it corresponds exactly. The negative parts of the gradient function are where there's a negative gradient on the blue function. Okay? The positive parts on the gradient function correspond to where there's a positive value of the gradient of the blue function. Okay? The points where there's the 0 points on the red function correspond exactly to the local maxima or minima on the blue function, and the POI, the points of inflection on the blue function, correspond exactly to the local maxima or minima on the red graph. Yeah? Exciting, isn't it? Whoa, look at that. So we got it right. Look at that. A funny quartic, okay, with a stationary point of inflection there at the origin. Okay, we start with our points of 0 gradient. There's one, and there's our gradient function. Oh, there's another one too at the origin, and there's the two red points are the gradient function, 0 points. Okay, now what else am I going to look at? Okay, I'm saying the gradient's negative there, and the gradient is positive there. Oh, right, in 2 spots. Yeah, okay. So therefore, the values of the gradient function are going to kind of correspond. They're going to be negative for the left-hand part of that, where the blue function, the values of x for which that blue function has negative gradient over on the left-hand side, and they're going to be positive values for where the gradient is positive of the blue function, and it's going to be 0 for where the gradient of the blue function is 0. Okay, now there's a point of inflection there too. It's a little bit harder to see, but yeah, gradient 0. And the point of inflection is about there. It's halfway between the cave up, that little dip to the first local minimum forms, and where it starts to go concave over to the right, if you know what I mean, pointing downwards to the right. Anyway, you have a good look at that, and you can see that is the point of inflection. And that's where there's a local maximum or minimum. Okay, I've worked it out. I've worked it out. It's a local maximum because I've got the trends right. And there's your shape. Cubic, a beautiful cubic. Very nice. And there it is. And you'll notice that cubic has, not only does it have a local minimum at the origin, but it's corresponding, it's got 0 value and 0. Yeah, that's right. It's a local minimum at that point where the blue function has a point of inflection, stationary point of inflection. So 0 value and local minimum. That's what I'm trying to say. Excuse me, I'm getting tongue-tied. I've had a long day, so never mind. This is fun. Oh my goodness! Look at that one. This is mod x, absolute value of x. Now you've got to be careful with these. The gradient is not defined at that cusp, the kink point. You cannot have a gradient at a kink point. The curve has to be smoothly changing from one gradient to another. You cannot draw a tangent at that point because it could swivel around just about any old way, okay? You just can't do it. So you do not define the gradient there. That gradient on the left-hand side is -1 because this is just absolute value of x, and the gradient is +1 there, so that's what we expect our gradient function to do. You've got, yes, that's what it's doing. Now, do you notice that I put open dots there at where x is 0? Open dots to reflect that the gradient is not defined there, okay? You must do that, otherwise you are wrong, okay? Yeah, open dots. Make sure you put open dots there. For heaven's sake, just put open dots. Now, that silly looking software didn't do open dots, so I'm going to draw them in. Yes, okay. That's it. Right, what's this? X squared minus 2. Well, that's simple enough. We know that that would get us a gradient function of 2x, but let's analyse it. Okay, zero gradient point, gradient negative, so therefore negative values for my gradient function of those values of x. Gradient positive, therefore positive values at those values of x, and there it goes. Now I'm going to make it really weird. Have a look at the next screen. Oh, no, that's not weird. That's just what we were expecting. Now it's weird. Now it's weird. Ooh, let's have a look at that. How do you do the gradient function of that? Well, don't panic. We'll get it sorted out. First of all, those kink points there, the gradient is not defined there. Do not do closed dots at those points because you'll be wrong. Yes, zero gradient point. Good. Now, look, the extreme left-hand side of this graph is unfiddled with compared to what we've just been doing. Okay, we've just been doing the graph of y equals x squared minus 2. So the bit that's been messed with is the middle bit. Okay, that's changed, and that's going to radically change our gradient profile, if you know what I mean. So yes, there's gradients negative there and there over to the right of the y-axis now. And the gradient is positive, yes, correspondingly in those two locations. So therefore our gradient function has got to reflect that, okay? Now I've drawn a few little dotted lines there to get myself sorted out. So because those cusps, those kinks are kind of like the point where the gradient cataclysmically changes, if you know what or you'll see what I'm trying to do in a minute. That's the line that I had on the previous graph for the gradient function, okay, for that part of the curve. Now, for the other side there, where it's unmessed with, that's what I got before as well. But look, in the middle, okay, to the immediate left of the y-axis, the gradient is now positive. It's now positive. So we've got to start doing positive gradient function values there, okay, positive, and leading down to 0 at where it crosses the y-axis, and then going negative in the other direction. So this is what happens. Ooh, that's very strange. Now, one thing we haven't done is we haven't done our open dots, and that's very, very naughty, so let's do them now. Good. Now, do you get that? Have a look at that middle part of the graph. You see what I'm doing? I'm saying the gradient starts off positive, becomes less positive until that blue graph crosses the y-axis with 0 gradient, therefore the 0 gradient function value there. And then as it crosses over into the positive x area, immediately right of the y-axis, the gradient goes negative until it gets quite negative, and then you get the kink point where everything turns around the other way again, and the gradient becomes positive again. Now, I hope I explained that all right. So you've got to be able to do that systematically, okay? Very systematically. Okay, you'll get it, don't worry, just practice, you'll be fine. But that's what they look like. Oh, there it is, okay, we got it right. Oh yes, I can't stand those missing open dots, I have to put them in. Oh, log, we're nearly finished now, I think. Now this is an interesting one because there's no point on that graph for where there's a 0 gradient, is there? No 0 gradients. Well, what else do we observe? Well, it's the gradient is always positive, and it's decreasing as x increases. So we need a function which starts off very positive, remains positive, but becomes less positive as it moves in the positive x direction. And here it is. Woo! There it is. So, and that's the actual. Okay, that's the actual. So that's that one. Now, one last one. I think I'm worn out. Yeah, that's a mod one. That's a mod one. It looks like mod minus mod of 2x. Okay, that's not so hard. You've got to remember that the gradient is not defined there at all. Okay, open dots required. On the left-hand side, the gradient looks like it's plus 2, and on the right-hand side, the gradient looks like it's negative 2. So I think we can just about go now, can't we? We can draw the gradient function, so it's just going to be plus 2 on the left, with an open dot at the kink point, the value of x of the kink point, and it's going to be -2 on the right of the y-axis with an open dot at the actual x value of the cusp, the kink. That's it. You got it. Okay, how do you feel? It's easy if you just do it systematically and if you practice. So just do some practice and you'll get mighty good at these, okay? They're rather fun when you get to know them a bit. They're not intimidating at all, and you'll feel just like, oh, that's the answer, and you'll feel, yeah, with open dots, and there's my friend. You'll feel just like him. He's feeling very, very happy with himself. All right, thank you for watching this exciting episode, and we'll see you next time.